If you watched Oppenheimer, you're familiar with the idea that compacting fissile material may trigger a runaway chain reaction, releasing immense energy. This naturally raises an important question. Could something similar happen in a nuclear reactor? Owing to the fuel they employ, fast-spectrum reactors are particularly sensitive to fuel compaction. If this fuel compaction occurs during an accidental sequence, it may trigger a runaway chain reaction and lead to the disruption of the reactor core, what we call a core disruptive accident. Ensuring the safety of such systems requires a deep understanding of both the likelihood and consequences of these events. Yet, there's been limited research on this issue for one specific reactor type, the heavy liquid metal fast reactor. My PhD research was performed with the goal to fill that gap. To establish a condition for the fuel compaction to take place, a hypothetical scenario is studied where a full core blockage leads to the failure of the structural material and formation of a blockage above the fuel. The coolant flow then compacts the remaining fuel against this blockage, increasing the system reactivity beyond the prompt critical level and thus the system power. This will cause fuel melting and vaporization of both the fuel and coolant. To analyze this complex sequence, a dedicated multi-scale, multi-physics simulation tool was developed from first principles. It models reactor kinetics on the scale of a degraded core, fluid dynamics at the scale of its spherical shell, and heat transfer at the level of individual fuel fragments. These models are subsequently coupled to offer an integral view of the entire sequence. By employing this model, key physical mechanisms that drive a core disruptive accident in a heavy liquid metal fast reactor are identified. While the majority of the fissile energy remains within the fuel and only a small fraction is transferred to the coolant's high volumetric expansion coefficient helps mitigate the reactivity transient. Non-condensable gases also significantly affect the system's behavior during the expansion. Ultimately, thermal expansion of materials and the fuel melting and expansion terminate the reactivity transient, while vaporization leads to the disruption of the reactor core. This model also provides a conservative estimate of the associated energy release, about 160 joules per watt of nominal core power. This is nearly an order of magnitude lower than early estimates for sodium fast reactors, suggesting that heavy liquid metal fast reactors may have better response to such accidents. In fact, early estimates indicate that even in these extreme scenarios, the reactor vessel of Mira, a real design considered, will likely retain its structural integrity. By addressing a key gap in reactor safety analysis, this work supports the development of safer, more resilient nuclear technologies for the future.